So we've been talking about sequences and series. In the last video, we talked about arithmetic, sequences and series, and those ideas were arithmetic went up by a common difference every single time. A geometric sequence and series has, again, a very similar restriction, except for geometric, a geometric series exists if there is a common ratio instead of a common difference. So the word ratio is implying multiplication. Essentially, if you have a sequence, a pattern, and again, another fancy word for a pattern is a sequence, A1, A2, A3, A4, and so on, if there is a value R such that if you take A1 and you multiply it times R, you get A2. And you take A2 and you multiply it times R, and you will get A3. You take A3 and you multiply it times R. So the way you get to the next number in your sequence is you always multiply by some common number that never changes. All right, mathematically, you could write it this way as saying, well, if you take the first term and you multiply it by R and times R and times R, you're going to get A1 times R to the third. That's the fourth term. To get the fifth term, it would be the first term times R to the fourth. That would be the fifth term, and so on. Another way of finding out, so there's a couple ways of calculating R. Some people can see it using some mental math of thinking, what can you multiply to get from the first term to the second term? Another way is to take two consecutive terms and do second term minus first term, or fourth term, fourth term divided by third term. That'll get you the common ratio. That's another way to get common ratio as well. So that's our definition. Again, this is a very important vocabulary term for today. A geometric sequence has a first term. Everything following it is multiplied by the common ratio. So the first term, A1, doesn't have anything to do with the common ratio. They are totally unrelated. A1 is your first term. Now, there is a formula to come up with a geometric sequence to get the nth term, right? That's what this is saying, AN. You're always going to do first term, all right, where R is the common ratio, raised to the 1 less than n. All right, 1 less than the nth term. And I will show you why that works on the next few slides, why that n minus 1 is there. All right, so here are some examples of common ratios. You may have seen this before. Here, this is just multiplying by 2 every single time, times by 2, times by 2, times by 2, and so on. Times by 2, whole way up. Here, your first term, now we got to be careful. This could be written, so essentially your common ratio here is 3, right? Your common ratio is times 3, times 3, times 3. But if you notice, this formula doesn't have the n minus 1 in there. But it also doesn't have the 12 in there either. So one way to write this would have been 12 times 3 to the n minus 1. That's a correct way to write this formula. These two are equivalent. Right? Now, why are they written differently? Well, what if I broke down 12 to 4 times 3 times 3 to the n minus 1? Well, this is 3 to the first, and this is 3, and I could actually combine them, and you could call this 4 times 3. When you add your exponents, 1 plus n minus 1, these cancel, and you end up with 4 times 3 to the n. Another way of writing it. Here you would have a geometric sequence. Your geometric sequence here, you are multiplying by negative 1/3. Yes, you can have negative common ratios. Right? When you do that, you know right away if your common ratio is negative because the sign changes every single time. All right. So, pose a little question to you. Is AN equal to n squared geometric? So if you write out the first few numbers of this pattern, and I shouldn't need to go any further than this, is there a common ratio? And you should be able to prove to me yes or no. And right off the bat, I would say, all right, well, to get from here to here, I would need to times by 4. So to times by 4, I would need to do that everywhere. And if I times by 4 again, not working, not getting to my next number. So right off the bat, there is no common ratio. The answer is no, this is not geometric. The first three were, the last one was not. Write the first 5 terms of a sequence whose first term is 3 and has a common ratio of 2. Well, I told you the first term, so I only want the next ones, the next 4 after that, and every single time you are multiplying by 2. So that means 3, 6, multiply by 2 again, 12, multiply by 2 again, 24, multiply by 2 again, 48, you keep going, 96, and onward from there. But every single time, multiply by 2. If you had to come up with a formula for this, AN, first term, 3 times the common ratio to the n minus 1. There's not a lot of work to the formulas. And if you don't believe me, you're welcome to plug in n equals 5. You'll get 48. 3 times 16. Okay. Find the 15th term of a geometric the geometric sequence whose first term is 20 and whose common ratio is 1.05. All right, 15th term. So now here's where the formula comes in handy.